Welcome back to the session. So this is IR spectroscopy continuation. I'm going to explain in this video. Right. So as I said you in my previous video lecture, epsilon of j into j plus 1, j is nothing but rotational quantum numbers. As they are quantum numbers apart from rotational energy levels 0, 1, 2, 3. Hence we got 0, 2b, 6b like that. And the difference lies only to like 0, 2b, 4b, 6b, 8b like that. Hence the difference is only to polar schematically represented. Now in this I am going to explain about quantization of vibrational energy levels. So whatever it may be, we are supposed to get borrowed from Schrodinger only because we already derived all the energy levels. Right? So from this Schrodinger equation for vibrational motion, vibrational energy level is given by EV is equal to hp into mu plus half. So mu is nothing but a vibrational quantum number. Vibrational energy, of course, this is vibrational quantum number also. Like other quantum numbers, it also have 0, 1, 2, 3, 4 like this, etc. So at 0 point means mu is equal to 0. At epsilon of ground state 0 is equal to half into hp. So the spacing between adjacent vibrational states, you can say E1 is equal to E2 is equal to like this. In a generalized form, you can calculate at least 5 up to 5, 0, 1, 2, 3, 4, 5 like that, and calculate E1 minus E0, E2 minus E1, E3 minus E2 like that you calculate, and then frame this generalized statement delta EV is equal to h mu for any type of mu is nothing but vibrational quantum. So this is about little bit introduction to the IR spectroscopy. So the IR spectroscopic process, there are two types of bond vibration, right? One is stretching, second one is bending. So these are all stretching. So vibration or oscillation along the line of the bond, right? So this is original molecule, let us suppose say, right? So this is symmetric. Both sides it has been stretched equally. Hence this is symmetric stretch. So this is another case. This is stretching one side long, one side short. So that's why here you can see this arrow mark point. This is asymmetric. This is about stretching vibrations. So in case of bending, vibration or oscillation not along the line of the bond. Right? So in case of bending, this is in plane, means within the plane itself, scissoring, rocking. In case of out of plane, twisting and wagging. Right? So in plane, scissoring and rocking. Out of plane, twisting and wagging. So scissoring means simply you can say scissor like this. So what is scissor? You are supposed to do like this. So here in this case bending, right? So it means bond angle is going to be changed in case of bending vibration. So in case of stretching, bond length is going to be changed or varied. So this is harmonic oscillator IR spectroscopy based upon the Schrodinger derived energy levels, right? So this is actually parabola, but where is the second one? This is the realistic one. So vibrational energy, vibrational quantum number 0, 1, 2, 3, 4, 5 like this, right? So 0 to 1, 1 to 2, 2 to 3 like this. This will happen. And generalized resistance is said to here. Delta EV is equal to hv. That one you can calculate from this graph. Right? Next, degrees of freedom. So consider a molecule made up of n atoms. Mass of atom is concentrated in its nucleus and is very small in size. Therefore, atoms may be considered as mass points. So, to represent each mass point, we require 3 coordinates. Hence, to represent n mass points in space, we require 3n coordinates. This one, please remember, this is the basic point which we need. In case of degrees of freedom, number of independent coordinates required to specify completely position and orientation of a particle in space. This one actually you can understand realistically when you take an example. So, these are all generalized. Just look at this. How many types of degrees of freedom are there? Translational, rotational and vibrational. So, atoms. For linear molecules, this is the formula. Right? For non-linear molecules, this is. Right? So, translational, all are equal. If you see a rotation, it is going to increase one by another. In case of vibration, for atoms, it will not exhibit any case. Rotational vibration is not applicable for atoms only. It is applicable for molecules. Molecules are 2 types, linear and non-linear. In case of linear, this is 3n minus 5 and non-linear, this is 3n minus 6. IR spectrum, x-axis wave number, y-axis transmission. So, what is the main advantage or you can say application of IR spectrum means, apart from bond length and bond angle, it is able to detect the functional group region. What is the functional group region? It lies in between 1500 to 4000 centimeter inverse. In case of fingerprint region, it is 500 to 1500 centimeter inverse. So, you have to remember these 2 points. Most of the time, you will be getting in objective also. Right? So, lighter atoms will allow the oscillation to be faster. Higher energy, this is especially true of modes of hydrogen, of carbon, hydrogen, and oxygen. So, this is about the order, triple bond greater than double bond greater than single bond. It is affected by 2 primary factors when vibration is stretching or bending. Electronegativity difference of atoms involved in bond. For both effects, the greater the change in dipole moment in a given vibration or bend, the larger the peak. The greater the difference in electronegativity between the atoms involved in bonding, the larger the dipole moment. For example, if you take HCl, HBr and HF, which will have more dipole moment, obviously HF, because fluorine has high electronegativity. So, typically stretching will change dipole moment more than bending. So, dipole moment is the foremost criteria. From here, these are all for knowledge sake only. That IR spectrum, each stretching and bending vibration occurs with a characteristic frequency of the atoms, and charges involved are different for different bonds. X-axis, y-axis. So, this is all as to gain knowledge only. This is IR spectrum in terms of wave number. Hc mu bar. R bar is equal to Hc by lambda or whatever it may be. Wave number means centimeter inverse. The 4 primary regions of IR spectrum: hydrogen bonds, triple bonds, double bonds, single bonds. Here you have to categorize this region. So, fingerprint region will come in between 600 to almost up to 1600. Right? So, double bonds, it will range from 1600 to 2000. Right? So, from 2000 to 2800, we are going to notice the triple bonds. From 3000 to 4000, we are going to notice the hydrogen bonds. This is very, very important. So, for this, simply by taking few examples, the graphs were shown here. Alkanes. So CH stretching, right? So here this bond, it lies CH2, ending are CH3, in between are CH2. So CH2 are 1450 to 1470 and CH2 is 1360 to 1390. So here all these carbon and hydrogens are sp3 hybridization, and in this it is 2000 carbon and hydrogen. This is 2800 to 3000 inverse centimeter. So like this you consider ethyl benzene, right? CH bonds, they will have the region between 3000 to 3100 centimeters. In case of C double bond C, because here you can see benzene C double bond C, 1500 to 1600 centimeters. So this CH, this is 3000 to 3100 centimeters inverse, because we are considering in terms of wavelength. So this is another example, butanol. So here butanol means OH. This is 3200 to 3400, and again this CO stretching 1050 to 1260, and here band position changes depends on the alcohol substitution. If it is primary, if it is secondary, if it is tertiary, and if it is with phenols, this is the variation. Like this, one more example of cyclohexane carboxylaldehyde, right? If I take alternative double bonds here, simply I can call it as benzaldehyde, but here there is no double bonds, hence it is cyclohexane carboxylaldehyde. So here C double bond group and sp2 hybridization, CH stretching, doublet, and it forms at 2720 to 2820. So this is all almost fixed, you are supposed to remember. This is one more example, 3-methyl 2-pentane. So CO stretch at 1705 to 1725 centimeters, right? So with this, IR spectroscopy is completed, right? So next we are going to learn about NMR spectroscopy. Thank you all. We'll meet again in the next video.